seal. Ingmar Bergman, you know, it's very famous because he also married. I cannot tell you everything, but too many things. Go ahead, guys. It's,
okay.
It's the story of because it's connected also to the Italian cinema, right? So Italian cinema during the 1960s and 70s, it was a very important period of Italian cinema. So please go see something. But go ahead.
Okay, Alice is in a good movie folder from Barry. Okay.
Go ahead, guys. Go ahead.
Okay, so I'll talk about the singular value decomposition. And here we start with SVD, or what it does break out down to rating matrix is I'm very sorry, I don't know how to read that. Is it art equals
singular values, right? Singular values. Yeah, latent. Which one you don't know? Latent.
I mean the second line. I don't know what it is.
Oh, you use sigma V transpose, right? So there is a rating matrix R, and you decompose it as U, which is a matrix of eigenvectors. These are the left eigenvectors. Sigma is a diagonal matrix that contains the eigenvalue, and V is the matrix of right eigenvectors of the matrix R. Okay? So the matrix U and V, they are unitary matrices, right? So the unitary matrix, it's a matrix such that if you multiply the matrix by itself, you obtain an identity matrix, okay? So they do not need to be square. But yeah, so these are the properties. Go ahead.
I regret watching comics in high school, but anyway.
You didn't know me then. You didn't know me then, right? If you had known me, I would have told you to study this. Go ahead.
Okay, very sorry. So it breaks down into 3 parts. This helps us to find the hidden patterns that connects users and movies. For example, similar taste or preference trees. By reducing noise in the data, SVD improves prediction accuracy. We can better estimate how a user might rate a movie they haven't seen yet. In the table below, you can see as we increase the number of latent factors K, the RMSE and the MAE value change, showing how model complexity affects accuracy. In short, SVD helps reveal the hidden structure behind our movie ratings. Okay.
Let me stop you there. Look at the last row, right? Both for the RMSE and the MAE, they degrade when you take too many factors, okay? I don't want to break your... I don't want to... my point is not to put you in a tough spot, but do you have some ideas as of why the performance degrades when the number of factors increases? It shouldn't happen, but it does happen. Any idea why?
No, sorry.
Anyone in the group has some ideas?
I think because SVD is we do a low rank factorization, so maybe a small k is already approximate the R well. So if you have a larger k, it wouldn't make it better, I guess, because it's a low rank factorization.
But still, as k grows, the performance can only increase because you let's say you preserve more of the matrix. The point is that is what I told you many times, but you guys don't listen to me too much, which I understand. I also wouldn't listen to myself. But basically, you see the matrix sigma, right? The eigenvalues. When you run the algorithm, you collect the eigenvalues from the largest to the smallest. Okay. So the first eigenvalues, they are large and they are far away from 0. And as you go and pick smaller and smaller eigenvalues, what is left are very small eigenvalues. And what we said is that small eigenvalues are associated with numerical instability. So I think what you're observing here is the effect of numerical instability. Okay, because as k grows large, You collect small eigenvalues, and they produce. The numerical instability gives you an approximate solution to the decomposition of the matrix, right? So you don't do a good job anymore. Go ahead.
So after applying SVD, we got feature vectors for each user. To visualize them, we use PCA to project these features into dimensions. What you can see here is the projection. Each dot represents one user, and the color shows uh, 8 clusters, groups of users who share similar movies preferences. The central area reflects more common taste, while the outliers indicate users with very unique preferences. So this plot gave us an intuitive view of how SVD captures hidden relationships among users, turning complex high-dimensional data into meaningful visual insights. Okay.
Okay, so now I'm going to talk about PCA. So in our data set, each user gives ratings to many movies, right? So sometimes hundreds of thousands. So let's mean that each movie is originally treated as one separate dimension. So the user rating matrix is very high dimensional and very sparse. So now I'm going to talk about what is PCA. So PCA finds a new set of axis that captures the largest variance in the data. So you can see from this picture, we start with the original XY, and it represents 2 raw rating dimensions. But the data points are like, you can see that it is scattered. So the original axis may not reveal the real patterns. So PCA can find new axes. So shown here as PC1 and PC2, the better explain of variations. So PC1 is the direction of the maximum variance, while PC2 is the second most variance and orthogonal to PC1.
Correct. The orthogonal is the crucial part, right? Orthogonal is the crucial part.
So now in my codes, I use PCA from scikit-learn. And this function actually performs several important steps internally. So the first one is that it centers the rating matrix. So which means that it subtracts the mean so that rating are measured relatively to average preferences. Then it captures the covariance structure, which is how movie ratings covary across users. Then it performs singular value decomposition under the hood, which is SVD. Then it outputs the principal components. Next. Okay, so now we understand how PCA transforms users into a latent taste space. We can analyze the user clusters formed using k-means on the first 2 principal components. So you can see in this plot, each point represents a user project into a 2-dimensional space defined by the top 2 principal components of their movie ratings. So users who appeared close together tends to have like similar viewers and rating patterns, while users far apart represents distinct taste profiles. So here we applied k-means clusters with k equals 5, and each color here represents a different user cluster. Next.
Wait. So go back one. So we didn't do k-mean clustering together yet. Maybe I'll tell you now. Later you will see if you agree with me. So in this case, when you do k-means clustering, you see the separation between 4 and 0. You see that it's a straight line, right? So that usually means ballpark means that you have too many clusters, right? Because it means that the clustering is, because that clearly is one cluster by itself, right? So it means that you have too many clusters, and so the algorithm ended up splitting the one cluster in 2. So how did you end up with k equal to 5? Did you do an explained variance? Or what did you do for the k equal to 5? How did you get to the 5?
Actually, I just looked at this plot, and I seen that there are some parts that really have many dots and some parts that are not many dots. So at first I choose k equals 3, but it didn't distinctly separate the things. So I think that, so I choose k equals 5 is a better number for me.
Okay, understood. Yeah, go ahead.
Yep, next. So here to understand what each clusters maybe represents what they do, so we analyze the 2 key statistics per movie genre. So the first one is the count, which is how often users in the cluster watch a genre. And the second one is mean ratings, which is how much they like the genre, the average. So for me, I think that if someone has high counts plus high ratings, it means that in this cluster, they really have a clear preference. And with maybe high counts, but plus low ratings, means that it watches a lot, but it's critical to it. And while if it's low counts plus high ratings, it's selected but appreciated. So based on this joint analysis, we can meaningfully interpret each clusters. Like for cluster 0, we can see that this group watched large number of like drama, comedy, actions, and consistently assigns high ratings on them. You can see from the mean ratings. And they also scored documentaries, war films, and film noir exceptionally well. So I think that these users favor emotionally depth, narrative complexity, and classic cinema. Like these people maybe like movies like Shawshank Redemption, kind of that things, deep. And in the cluster 1, you can see that this group frequently watches popular genres like drama, comedy, actions, and adventure, but assigns lower ratings on average compared to other groups. So I think that they consume mainstream content, but tend to be hard to impress. So these people are like I watch Netflix, but nothing is good enough. Like they like maybe Marvels and streaming contents, but really gives over 4 stars, like the kind of people, critical mainstream viewers. So in cluster 2, you can see that this group has lower average ratings across nearly all genres and does not show strong genre preferences. So I think that they may watch movies less frequently and with lower engagements. And next. So here in cluster 3, this group rates many genres highly, including drama, action, adventure, crime, sci-fi, romance. And they also enjoy documentaries and animations at a high level. So these users are maybe like open-minded and appreciate to a wide variety of films. Like maybe like movie fans who enjoy both Pixar's and Christopher Nolan kind of people. Like all things they love. They love all things. And in cluster 4, this is the mainstream, which is the largest group. The heavily watched that enjoy action, adventure, comedy, sci-fi, and ratings are steadily positive, but not extreme. So they represent general audience taste. They enjoy mainstream hits and genre-driven entertainments. Next. So here I put movies into the PCA space. So now each dot represents a movie. So we originally had thousands of movies, each with its own ratings patterns across users. So PCA reduces this into 2 latent dimensions, PC1 and PC2, so we can visualize movie similarities. So if 2 movies appeared close together in this space, it means users tend to rate them similarly. So they like sharing similar audience appeal to genre characteristics. Next. So here I see some extremes. So here is the PC1 extremes. So with the high PC1 scores, you can see that like Casablanca, it has a mean rating of 4.42 stars. And like Chinatown has like 4.21. So these external movies reviews confirm that this PC1 axis reflects narrowly depth, artistic craft, and massive influence. Like I have searched for some things that some people said about these movies. Like Casablanca said that it's a timeless emotional power, and like Chinatown is the landmark in American cinema, which is all really good reviews. But now you can see that movies from low PC1 tends to be big budget flops, and you can see like Wild Wild West has a mean rating of only just 2.2, and like Congo 2.88, and some critics reinforce this interpretation. Like someone said that Wild Wild West is a comedy dead zone, and like Congo is an effects overstory.
Yeah.
So thus PC1 maybe separates art versus superficial spectacle. They also align strongly with average ratings. Next. So now here I see PC2, and you can see that in the low PC2, you can see some movies like Natural Born Killers, Ice Wild Shut, and these movies tend to be like darker, intense, or psychologically heavy. Like Natural Born Killers are like violence median, and Eyes Without Shadow are like psychological drama. And like, but you can see that high PC2 here, you got Mel, the Santa Claus, like Jumanji, which is the only movie that I've watched. And so these films are related, relaxed, humorous, and maybe more emotionally light.
Nice.
Yeah, so you can see that PC2 maybe represents a serious and cheerful emotional axis. So together, PCN uncovers a cultural map of film taste that matches human intuition. Next.
So now we come to the non-negative matrix factorization, which we have also done on this movie dataset. So non-negative matrix factorization is the idea that we try and describe our user ratings of movies with two matrices that are grouped in groups of K, which in my code is called factors. So there will be one matrix, the W matrix, which will be assigning a user assigning weight for one user to these different factors, and then another matrix, the H matrix, that assigns for each of these factors, assigns each movie a weight on these. So we cluster or we divide our matrix into groups, sort of hidden genres, and then we can try and look at those and see what our model finds.
I think I mean, it's in the title, right? Non-negative. So the entries are non-negative. I mean, let's stress this. Yeah, go ahead.
Yeah. But the model only works with non-negative values because when I haven't put in the mathematical formula here, but everything is absolute values. So if you had negative values, those wouldn't be reflected. But of course, for movie ratings, you can always it's relative, so it's 0 to 10, 0 to 100, whatever. So therefore, a negative sign wouldn't matter. What we see when we do this for different K values is that it's pretty easy to interpret what these different factors are. So I've plotted the top 10 movies with their strength and the strengths in the H matrix. So for example, factor 2 with K equals 5, we find that there is a genre that is basically just movies, classic movies from the 90s. While if we increase the factor of 10, we can get a lot more specific, with one of these factors being George Lucas movies, James Cameron directed movies, and Steven Spielberg directed movies, which is a lot more specific. So we see already here that if we try and increase the K, we will get a lot more specificity in these different genres, which of course can both be a good and a bad thing. So I haven't included this in the slides, but if you calculate the RMSE for our predictions, then you will find that as you increase K, it will just steadily decline. It doesn't really ever seem to approach a single value. It would always just steadily decline a little bit more and more. So there's definitely some returns if you increase the K, but you probably also end up with a problem of overfitting, where each K just results to one user.
I mean, that's extreme case, right? So when your K will be the full number of movies, that's what happens. That's one factor per
Yeah,
Very
exactly. Next slide. Oh, yeah, we also find that while we increase k, we will also still find that some of these factors will be the same. One thing that I noted is that you will find that a lot of movie series, so Lord of Rings is an example. You find that they will be clustered together, but it's not really useful in a model to have that, oh, this guy liked the first one, maybe he'll like the second, the third, the fourth, and the seventh one. If we want to use this model for giving recommendations, it's a little bit useless giving a recommendation of, oh, you liked Lord of the Rings and the Fellowship of the Ring, maybe you would like the Two Towers also. That's kind of redundant. So what we also want to do is we want to try, and next slide, regularize our model, which would mean that we try and put a lot of zero values on it. I did this both for L1 and L2, and we see that it's we should not really have a high lambda value in these, as then we just get complete sparsity in W and H. This would not be very it just leads to the model breaking down, and you can't really use it to predict anything. So a very low lambda value, and we also, of course, see that as we increase the regularization factor, we also get a higher RMSE, which is expected as we try to minimize overfitting. And of course, overfit model would still have a high RMSE, a low RMSE, as it would, of course, be overfitted. So next slide. So if we try and compare these different groups of these different factors of either a dense model, which means no regularization, and then a sparse model, which means that we have now reduced some of the number of movies, we find that with L1 regularization, that we kind of remove these series. So like Lord of the Rings, The Return of the King, and The Two Towers, they are given less weight as they are the same, and they are actually somewhat removed in the factors, even though all the other movies stay the same. So it values less the serialization of movies. And I also tried doing this for L2 regularization, but it did not work, as it would constantly in the sparse model, no matter the lambda value, by the way, give the exact same answer always. So
because the weight goes down, and yeah, understood. Yeah. Let me think a second about L1. Let me absorb this a second. So you're saying, so latent factor 2, latent factor 4, dense versus sparse. Sparse is language to 0.5, and what you're saying is that tell me again, right? So if I go to the dense one,
I would say the best example is factor 4. Like I did this for this is all for k equals 10. I just found that was not too much and too little. Yeah, sweet spot. I didn't have any good way to evaluate it, but I just looked at it and thought, okay, now we're getting into specificity, and I also have stuff to look at. But if you look at this factor 4, most of the movies are the same. Correct. Like you have Fight Club, Shawshank, Matrix, Pulp Fiction, Usual Suspects, which are all in both factors. However, in factor 4, you also have that The Return of the King, The Fellowship of the Ring, and The Two Towers, they would all be recommended. But in the model, they should more count as one, because they are indeed one movie. And while it is then left out of factor 4, I would still say that a factor 4 would be a better model, as it would.
Yeah, but you don't have only one of those. Yeah, that one ends up in some other factor, right?
Yeah. You can actually see that it does in factor 2. That's where Lord of the Rings: The Return of the King has.
I see.
Left, top left corner.
Yeah, that's what I was wondering, right? Because did you need to match the factors from one decomposition to the other, like seeing which movies from one factor appear most in another factor, or when they come out where they were ordered correctly? Do you remember?
They were mostly ordered. You would
almost ordered.
You would find sometimes they would. I mean, of course, when you change the k value, they would not be ordered the same. But when the k value was the same, they were mostly the same also. Like,
Okay. So if you change the lambda, but the case stays the same, the ordering also remains the same. Roughly.
Yeah, that was at least what I mean, it's, again, I've only been able, for this slides, it would be impossible to show all 10, or at least not impossible, but very boring. So these are example, and they were the ones which highlighted mostly my point. But you would find the same trend in others, where it would be that they would either be the same, where like they wouldn't change, or they would have some smaller movie changes.
Excellent.
Okay.
Excellent.
Next slide. Okay.
Yeah, go back one. Let me absorb it a little bit. It's such a nice slide. Go back one, please.
Okay.
Yeah, because also there, the Star Wars movie, they are still there in all the sparse one, right? But yeah, maybe, who knows?
Don't look at the L2 one.
Sorry, I'm talking about bottom right. It seems that there should be some other. I'm trying to see which movies are preserved from one factor to the other, and it seems.
But in the L2, which is the bottom ones.
Yeah, that's it.
No matter what I did, what I did, the movies in the factors would be the same always. It would be the same order: Forrest Gump, Pulp Fiction, Matrix. This would just stay the same. And if I changed it to 0.05 lambda, still the same result. It didn't really matter.
Understood. This is what we discussed in class, right? The L2 regularization is very, very smooth, and so basically you never got anywhere useful. Okay, now I'm happy. Go ahead, please.
Okay, next slide. Okay, then we tried doing some clustering, and as you mentioned for the PCA, is there a method to determine the optimal K? Yes, there is. It's there's more than one. As my research called ChatGPT, there is more than one method. I wouldn't say that I understand this, but of course it's important to determine the optimal amount of clusters. As like if we would try to sort a Skittles bag into a certain amount of clusters by color, it would be weird if we had more clusters than there are colors, and it would also be weird if we had less clusters than there are colors. There is an optimal K, and in this elbow method, what you try to do is you try and find the point, the least number of Ks where where this inertia has stabilized and has approached its final value. So,
if I look at this plot, for me there is no elbow, meaning that the decay is very, very smooth. Usually, if you had to do it for some other data, then you will see a larger jump after, let's say, 5 components, 6 components. So this one here tells you that the clustering is not successful in the sense, right? That the information, very, very roughly, right? But the size of information per K is decreasing very slowly, right? So the algorithm keeps finding something, but of course I understand that you choose a certain number. Go ahead.
Yeah. I mean, if you chose this shows the one without regularization, so for the dense one. Now, if you did the same plot for the sparse one, there was actually a little bit more jump around 5 to 6. But of course, when you look at the actual clustering plot, it also, especially for the sparse one, it becomes really hard to see how it actually clusters it, because it's mostly just a straight line. There are some other clusters which was basically just singular uses in which I thought maybe it was harder to see the actual difference between these 2 plots if I made the whole scale a little bit bigger. So there are some singular uses that has been excluded, which count as a cluster in this model. But what you end up seeing is the same trend line, but that the regularization has completely flattened the line with very little variance. And then how you determine this, which one is a cluster and where the cluster ends and starts, it becomes really, really hard. I mean, it's just a straight line. Where does cluster 1 start and where does cluster 2 start? That's not really easy to determine compared to if you had one that like one amount of data at one part of the plot and one amount of data in the other part of the plot. But yeah, what you see is that with the regularization, you really, because we have we remove a lot of movie factors, it becomes very very flat and very, very linear, the clustering. Yeah, next slide.
We don't hear anything. I don't know if somebody is...
Philippe?
Philippe?
You here?
Hello.
Is he here?
I think he's here, but maybe it's his mic.
Is he normally just called Philippe in Google Meet? I don't know. Yeah, he is, because that's when we have meetings. Is he just not here? So, I mean, I guess we have a little bit of a problem.
You want to check with him?
I mean, we talked yesterday. He was here yesterday when we were making the slides and ensuring that we had done our work. So I think it's a little bit weird that he's not here.
I don't know if it maybe drop off of the meeting. I don't know. Yeah. Do you want? I'll give you a second to check. Maybe you can get to his phone number or something.
Maybe because the typhoon, it got the connection for the Wi-Fi. I'm not sure.
Because he's not in Shinju. Is he? Is in the Philippines?
I think I saw him once in my dormitory, but I never talked personally.
I'm not sure if it was him or someone else. Yeah, guys. Decide the strategy. You want to wait for?
Or I just maybe say the conclusion first. It will say a little about the PMF.
Let's go back to presentation mode then, guys. Yeah.
Okay.
I think I need to share something else once you go in presentation. Let's see. Okay. Yeah, just close the window. Yeah, go ahead. Go ahead, please.
So maybe I'll wrap up with 4 slides that summarize 5 common matrix factorization methods. In the first SVD, we do a low-rank factorization of the rating matrix to obtain user or item latent factors. It's a stable baseline for rating prediction, but it optimizes the squared error, not ranking. And for PCA, it's essentially SVD on mean-centered data, finding direction of maximum variance best for dimensionality reduction and visualization, like PC1, PC2 to inspect the cluster. NMF adds non-negativity constraint, yielding additive or hard-based factor. So the interpretability is high. It's great for top picks. Regularized NMF is NMF plus sparsity. Like Booster says, is often L1. And you will got a cleaner, more concentrated topic, and often better generalization, but you need to tune the lambda. And PMF is Poisson MF, treats interaction as count. Implicit feedback with Poisson likelihood, naturally handling the unobserved not equal to 0. It fits highly sparse long tail like clicks or views for 1 to 5 but for 1 to 5 continuous rating, it may not be ideal.
Very good. So if the team member comes back either this time or either maybe next week, maybe if they tell him if he wants to present next week, because yeah, I think yeah,
okay.
It'll be a pity to miss it. Okay, very good.
Okay. So
good job, guys. Yeah.
Yeah, this gives the intuition, and I'll have 4 slides to conclude. And next slide align the difference in a compact table.
Okay.
And this is a comparison table. From this table, I'll call out 4 rows, which is data view, interpretability, strengths, and caveats. For the data view, SVD and PCA operate on explicit continuous value. MMF and Reg MMF require non-negativity. PMF targets count and implicit data. For interpretability, MMF is already high, and the Reg NMF is highest because sparsity makes the topic more, maybe I'll say, category-like. SVD and PCA are medium since the factor can be positive and negative. For the strengths, SVD is rating regression. PCA excels at reduction and visualization. NNF and the Reg NNF shines at topic or cluster explanation. PMF excels at implicit, top-in, and long-tail behavior. And there's some caveats. SVD doesn't directly optimize the ranking. And PCA must... Hi, is that Halib? Okay, no. Okay, PCA must center the data. NNF is non-convex and init sensitive. Reg NNF require tuning the sparsity, and PMF is not ideal for purely continuous rating. So if you remember these 4 lines, you can quickly place each method in your head. And next, which method should I choose? For selection, here are 4 scenario-based rule for thumb. If you need a stable rating regression baseline, you use SVD, and you may use masking or regularization when entries are missing. If you care about visualization or exploring clusters, you use PCA. It's the fastest way to plot PC1 and PC2 and see the big picture. If you need easy to explain or topic or genre-like factors, you use NNF. If you want a cleaner category-like topic, you go regularized NNF. If the data are implicit feedback like views, clicks, or the add to cart, extremely sparse and long-tailed, you use PNF. It's more appropriate than a square error model. So in short, match the model to the data and objective, not to a single metric.
Very good, guys. Very good.
So finally, we got 2 takeaways. The most important thing is that no one size fits all. Numerical accuracy, and interpretability, clusterability often trade off. If you're gonna align model with data type, the explicit rating, you use SVD or NNF or Reg NNF. The implicit or count interaction, you use PNF. If you need easily explainable factors, you maybe prioritize regularized PMF. And that's my concise wrap up for the 5 method. Thank you, guys.
Thank you. Yeah. Movie references are infinity, right? So there was also a very good Italian movie in the last slide. But you guys are taking advantage of my love of movies. Anyway. Okay, excellent. Yeah, as I said, if the team member that did the Poisson the Poisson model comes back, we will listen to him for sure. Okay, let's take a small break, guys. The usual 5 minutes. So we just stretch our legs, and I'll see you back at 16. Okay, guys. Okay, we still have a couple of minutes, guys. Well, maybe Group B, you can start sharing and yeah, tell us if you see the Seven Seal movie. Group B, Group B.
Hey.
Hello.
Hello. And then let me share my
Yeah, slowly. Yeah, we still have a couple of minutes.
Okay. Because our share slide got some problems, so my part is missing. So I use my backup PDF to present. Okay.
Yeah, go into maybe presentation mode or because right now you have to scroll back and forth. Try to go. Do you have Adobe? Maybe go. That's good. That's good.
Yeah,
That's,
is okay.
that's
And
good.
let me switch my screen.
Okay, very good, very good.
Okay. Hello, everyone. We are Group B, and I'm the person responsible for datasets. And today I will show our dataset, a unified evaluation pipeline and baseline results. Then I will wrap with quick takeaway and what's next. So our dataset is MovieLens 100K. It has 100,000 ratings on a 1 to 5 scale from 943 users over 1,682 movies. Each user rated at least 20 items. It's compact enough to iterate quickly, but standard enough to compare to classic CF papers. Notation-wise, the rating matrix is R proportional to R and times M times N, and M is 943 and N is 1,682. Most entries are missing exactly what matrix completion targets. To make models comparable, we use one evaluation API for everything. We slipped by user 8020, then report point-wise errors, MAE and RMSE, and top K ranking metric, precision at 10 and recall at 10 using relevance threshold more than 4. The same code path score every model. So the leaderboard is, oh, this is the previous one. And here are the numbers. Oh, here are our baseline models. We have global mean, user mean, item mean, and the truncated SVD, and K is 50.
Go back a second.
Yeah.
So the global mean is over. So you call it item, or why don't you call it movie? Okay, and got it. Item means movie, right?
Yeah.
Okay, go ahead.
And here are the numbers. SVD K50 leads with MAE 0.804. I take it as approximate, and RMSE approximate to 1.012. It also dominates on ranking. And this one PREC at 10 is 0.130. And REC at 10 is 0.132. Item mean and user mean are weaker, reasonable on RMSE, but almost no hit rate at top 10. Global mean is the floor, so even a simple truncated SVD already captures useful latent structure. And our RMSE versus NDCG at 10. This shows the trade-off between rating accuracy, and points near the top left are good. Our SVD baseline sits near that frontier versus the mean baseline, confirming that low rank structure helps both prediction, error, and recommendation quality.
So what is this NDCG? What does that stand for? Known? What is NDCG?
Oh, sorry, I used the wrong word. This one was from previous presentation. So because this is a backup one, so some pages are from previous challenge or something. Yeah.
Okay.
Oh my God, the title is amazing. Yes, and our takeaways are: the pipeline is ready. SVD K is 50. Larger than means across MAE, RMSE, and early top 10 metric. Next, my teammate will move to more details about SVD.
Yeah, go ahead, guys.
Yeah. 以后耶。
Just a minute. So am I going to show the slides or?
Yeah.
Okay. Then I'll show the slide just a minute. Okay. Okay, can you guys see the slide? Okay, so then I begin my part about SVD and then go into PCA. So SVD decomposes the rating matrix R into U, sigma, and V transpose, so we can approximate it with only K latent factors. Each K represents how many hidden features we use to describe users and movies. I tested K equals to 10, 20, 50, and 100 to see how reconstruction accuracy improves. This plot shows the reconstruction RMSE as K increases. As expected, RMSE drops when K grows. That means a higher rank approximation captures more variation and reconstructs rating more accurately. Okay, so let's move into the next slides talking about PCA. PCA is mathematically related to SVD. That means PCA performs SVD on the centered data. Both identify the direction of maximum variance, but PCA gives us interpretable principal components that explain the dominant rating patterns among user and items. Now, let's see what PCA reveals visually. Each point on the left is a user. The first principal component captures rating generosity, strict bit versus latent users, while the second captures taste differences, such as action-oriented versus drama-oriented users. On the right,
and the shape is kind of weird, right? It's so conical. Why is it so conical?
also, actually, I didn't put much more.
No, go ahead. It's so weird.
Okay. And on the right, each point is a movie. Movies close together are likely by similar audiences. For instance, comedies may cluster separately from thrillers. And next, to make the user structure clearer, I also applied k-means clustering on the 2D PCA coordinates.
Clustering on two coordinates, right? Okay.
Yeah. And each color here represents a distinct group of users with similar rating behaviors.
Yeah, as I said to the previous presentation, this clustering, so because you did only on two users, right? This clustering is not really meaningful to me, meaning that the data should appear already clustered. You should see that when you do the PCA, you should already see clusters, right? Here you're imposing just a uniform partition of the data into regions, and this is not really too meaningful to me, especially because you only use 2 dimensions, right? If you use more dimensions and then represented the clusters in 2 dimensions, then I could believe you. But if you just show me PC clustering over 2 dimensions, I'm very skeptical that this is meaningful. But go ahead.
Alright, so
you understand my point?
Yeah, understand totally.
Go ahead.
Okay, so this confirms that PCA directions really capture meaningful audience patterns. And so when we compare the reconstruction accuracy, PCA and FDD show nearly identical RMSE curves.
That's of course, yeah. That's of course. One is based on it, right? So no surprise.
And since they are mathematically equivalent for center data, that shows a increasing accuracy when the number of components increase. Okay, so here's the some summary takeaway and a briefly comparison between FVD and PCA. And both of them are beneficial for us to show the complementary views of the latent factors. So in brief, truncated SVD efficiently reconstructs missing ratings with lower RMSE at higher K. And on the other side, PCA provides interpretable access that explain users and movie variation. And K-means on PCA uncovers audience segments, turning latent factors into understandable behavioral groups. And now next, we are going to move to non-negative metrics factorization. And this part will be covered by a group member.
Okay, so I am going to talk about the non-negative matrix factorization.
If I could adjust your microphone a little, you sound like calling from a cave underground. Okay, try to stay closer to the microphone, please. Go ahead.
So is this okay? My voice is okay.
It's going up and down a little bit. Try to stay close to the microphone, and we'll try to adjust the volume. Go ahead.
So here our objective is to decompose the space rating matrix R into two non-negative matrices, W and H. This non-negative constraint is crucial for NMF to generate clear and interpretable things. And next page. In our execution, I set the maximum number of iterations to 500 to ensure the model achieve proper conversions. And we perform a comprehensive sweep from K-2 to K-3. K equals 2 to K equals 100. The root mean square error curve clearly shows that the minimum point occurs at K-17. Yield a test root mean square error of 2.6148. This represents the best predictive performance we can achieve within the NMF framework. Therefore, we select K-17 as our definitive analysis benchmark. And next page. Why do we emphasize NMF over SVD? The answer lies in the semantic purity of the factor structure. SVD are orthogonal with both positive and negative weights, making them difficult to interpret as a single cohesive thing. And NMF are strictly non-negative. This forces each factor to become an additive part-based topic method. For example, a movie's contribution to a hardware factor will only be a positive way, evading ambiguous interpretation like both liking hardware and disliking Shredder. This structural advantage allows us to accurately assign semantic labels to our latent factors. And next page. Next, okay. So here I use K-17 to run to select this factor and show the top movies of each factor. And here I choose some most representative and semantically pure factors. Here is the movies like Jaws, The Shining Cycle. Those are horror movies and or thriller movies. So No. And the next factor, and this factor we saw that the top movies are Beauty and the Beast, Aladdin, and like these movies are comes from Disney. So I think this thing might be comes from the children. And the next page.
No, wait. Apollo 13 is not a Disney movie. It's not a go back. Apollo 13 is not a family movie, right? I mean, I wish you've seen the movie, right? Apollo 13.
Apollo 13. Apollo 13. I just use the.
No, I'm telling you. I ask you if you saw the movie, because the movie is not a family movie.
Oh.
I'm not criticizing you. It's just a comment on the fact that Apollo 13 is not a family movie.
I don't take the. I don't see these movies. I just saw the top ones.
Watch Apollo 13. It's a beautiful movie about space, right? It's the tragedy of the Apollo 13 and how they fix the problem. I mean, it's yeah. It's a great movie. Anyway, go ahead. It's just a comment on the movie. Okay, go ahead.
And the next factor here. The factors are mainly Star Wars, and Star Wars. I think this is famous, and this is so. Also, the Return of the Jedi is also Star Wars. So this part, I think is I call this one the sci-fi factor, and that's it.
Okay. So next up, I will be covering the regularized NMF. So the goal is to understand how different strength of L1 regularization represented by the lambda affect three key aspects of this model, like the sparsity and the RMSE and the topic clarity. So I think the meaning of the symbol was covered, so I just put it here. So and I'll go on. Okay, so next page. So the data set was the MovieLens 100. Okay, and I split it into 80% training and 20% testing sets. Then we applied non-negative NMF with L1 regularization. Then we set the latent dimension, the K equals 20. And we tested in different lambda values, like 0, 0.1, and 1. And the max acceleration, we set it into 1000. So the model was trained using Python and scikit-learn. So in general, a higher lambda forces more coefficient in W and H to become 0 and increase the sparsity, but may reduce model accuracy. The next page. And here we can see the relationship between lambda, sparsity, and RMSE. So on this graph, the solid line shows the sparsity ratio, while the dashed line shows the test RMSE. So as lambda increases, we observe that RMSE rises, meaning the reconstruction becomes less accurate. And at the same time, the sparsity ratio changes notably. So showing how regularization affects the structure of the factor matrices. This plot demonstrates the trade-off between
interpretability and accuracy. When lambda increases, the model becomes simpler and sparser, but it also loses predictive power. So here we can see the lambda, when the lambda equals 0, the RMSE and sparsity is here. So here has the charge shifts. So in short, the model without regularization, that is lambda equals 0, achieves the best reconstruction accuracy, while large lambda values makes the model too sparse and less reliable. This confirms that strong regularization leads to underfitting, while a small amount of regularization can sometimes help. Next page.
Very good. Very good.
So this is, so look at the NMF model actually learned when lambda equals 0. So here are the top 10 movies in several components. So here, that's the table. So these clusters make intuitive sense and align well with the movie genres. So even without regularization, NMF can uncover meaningful and interpretable topics from rating data. So when lambda increases, these topics tend to collapse or become less clear, showing that regularization must be carefully balanced. Okay, next page. So to summarize, applying L1 regularization in NMF does help promote sparsity and can make the model simpler. However, too much regularization, such as lambda equals 1, causes the model to lose accuracy and topic coherence. So in our experiment, lambda from 0 to 0.05 seems to give the best trade-off between accuracy and interpretability. So for future work, we can test finer lambda values such as 0.01, 0.04, 0.05 for something else. And we can set the max iteration increase the max iteration for better convergence. Okay.
Hello. Okay, so I'm going to share the model share a PMF part. So
Can you try to speak up a little bit for us?
the PMF part. So in standard matrix factorization models such as SVD or NMF, we usually assume Gaussian errors and treat missing ratings as zeros. But in real recommendation systems, most missing entries do not mean dislike. They exist simply because the user has never seen that movie. Therefore, we adopt a Poisson-based approach that models the number of user item interactions directly. This assumption is much more suitable for sparse and long-tail data, which is common in real platforms where users only interact with a few items. Next slide, please. To make this is the implementation overview, and to make the results comparable with SVD and NMF, I applied a linear calibration step that maps PMF's output back to the original 1 to 5 rating scale. This allows us to evaluate all models under the same matrix. And next slide, please. Next slide, please. Well, this is the performance comparison. This table compares our 3 models under both full and sparse training conditions. Under the original dataset, PMF and NMF achieve similar RMSE and ranking results, while SVD performs the worst. When we simulate a sparse scenario by keeping only 30% of the training data, the Gaussian-based models degrade significantly, but PMF remains relatively stable. This shows that Poisson model is more robust to missing not a random situation because it does not interpret missing entries as zero. Although we can see that NMF slightly outperforms PNF numerically on precision and recall. Its underlying Gaussian assumption still treats missing entries as zeros. PNF based on the Poisson likelihood model's exposure rather than dislike. Therefore, even if its numerical scores are slightly slower, PMF is conceptually more appropriate and remains stable under extreme sparsity, showing stronger robustness in real-world conditions. And next slide, please.
A second here. What do you mean? Okay, what do you mean slim and original? Can you go back? So here you have PMF 50 and slim. What does slim means here?
It cut the ratings, like make the ratings missing to only there's only 30%.
Got it. So that's
yeah.
this. Okay.
Next
so
slide, please.
You move. So the idea is that you move more data from the train to the test to see how robust it is. Go back a second. Please. Can you go back one slide? So the original. Which one do you say that the NMF is better than PMF? Because here it's always better. No, come again. Which one is? Go ahead. Can you repeat?
You mean repeat which part?
At some point, you said the NMF is better than PMF, right? With respect to which?
It's like you can see the slim part. Compare the slim part and the original part. Like PNF doesn't, NMF doesn't change a lot. Still change, but like PNF changed more than NMF in this.
Got it.
That's it. But actually, theoretically, PNF is more appropriate.
Understood. Yeah, because but of course it's harder to train, right? So you're paying a price for the complexity as well, right?
Yes. Okay, next slide, please.
Good.
I forgot to save the plot after I run the code, and I don't know why it can run now, so there's no plot, and I will just talk about the result. So
okay. Put it in the final report.
We visualize the learned user and movie vectors using PCA for dimensionally reduction and k-means clustering. In these plots, the PMF embeddings display much clearer genre-wise separations. For example, action movies and romance movies naturally cluster apart. And quantitatively, PNF achieves the highest MI and purity scores, which means its clusters are more consistent with the real general labels.
Can you tell me what is NMI and ARI and so purity? We know ARIA is that Arimoto. What is ARIA? ARI?
ARI.
Information criteria. Now what is? You have three measures: NMI, ARI, and purity. Purity, I know. What are the NMI and ARI?
ARI, adjustment index and the normalized neutral.
What does it stand for? Newton. What is it? What does it stand for?
The adjustment index is the index minus expected index over max index minus expected index.
This is NMI or ARI? Which one is this?
This is ARI, and NMI is NMI is 2 times. It's quite complex. I'm not really sure how it works because I complete this part with GPT, and it's like it means like measures the information overlap between the predicted clusters and true categories.
Okay. Okay, good. Yeah.
Okay, so next slide, please.
Yeah. NMI is the mutual. Sorry, is this one here? So it's the mutual information, right? So ARI is the adjusted rank index. That's what you just said. And NMI is the normalized mutual information. Okay, good.
Okay.
Go ahead.
Okay, so this slide is like the code start and discussion. PNF still requires at least one interaction to learn a user's vector. So it faces the code start problem for completely new users or items. However, overall, Poisson matrix factorization provides a more reasonable and stable approach for handling sparse and implicit feedback data than Gaussian-based models. In summary, by modeling interactions house rather than assuming Gaussian noise, PNF better captures users' hidden preference and long-tail behaviors. It achieves higher recommendation quality and stronger thematic consistency in sparse scenarios, making it a more realistic alternative to traditional Gaussian models. And next slide. This is our work distribution. And next slide, please. And thanks for listening.
Yeah, so can the team leader tell me a little bit how was the group, how was the cooperation? Was it easier this time that you guys chose each other's for the group? Yeah, just tell me a little bit. Huh? Can the team leader tell me a little bit how was the cooperation this time? Hello?
Yeah.
Yeah.
About our cooperation this time, because our collab and Canva got some problems. So for my part's data set, some storage problem because some members use my function in part 1. So after the data is broken, some of their code cannot run. And for our Canva, my slide for part 1 has accidentally deleted by our member. Yeah, that's our disaster this time. Yeah. So
you guys are from the same dorm, right? So you guys are in the same dorm, right? So did you guys meet in
so we
person?
try to fix this problem last midnight. Yeah.
Very good.
So next time we will maybe open a copy or a backup online Google Drive to prevent this situation.
Very good. So as the leader, were you criticized for not taking these measures before the disaster happened? Were you held responsible? Were you held accountable by the other team members about this failure of basic file organization protocols?
I think this is the first time we face this problem, so we can learn a lot from this. Yeah, we learn experience.
Okay, very good. Okay, good job, guys. Yeah, no particular comments. Yeah, can you I'll just tell you a little bit. Can you go a little bit just one of these PCA plots where you have train and test? Can you just go to one of these plots a second? Yeah, can you share again the slides and go to the PCA plot, one of the PCA plots that you had?
Okay, just a minute.
I just want to say something.
Okay.
Yeah, just go back a little bit. Let's find just the plot. Go. Another a plot where you have train and test for PCA. Can you find one? Keep going, go forward, it should be there. Go forward. Ah, yeah. Keep going. Yeah, it should be here. Yeah, go back one. So this for me, it took me a while to decide whether this was good or not, in the following sense. When you do PCA, right, this is a supervised type of approach. So in a sense, if you leave out part of the data to the calculation of the PCA, then you expect the PCA calculation to not be good. So usually people will not do train and test in this way for deciding the number of latent vectors. What people will do is they will look at explained variance, right? So for example, for the PCA, you will see the error between the reconstructed matrix and the original matrix, and you will see how this loss looks like, and this will generally make some sort of an elbow, and they will use the elbow method to decide how to choose K. Okay, so this is not a bad idea, okay? Because you're saying, well, if I still remove some of the elements, my PCA calculation should still be resilient to these missing elements if really the latent factors are there. Yeah, just maybe, yeah. No other comment, basically. I just want to say this. Usually people use the elbow method instead of using the 80-20, because sometimes you really need to observe all of the elements in the matrix, and you see it as a matrix approximation instead of a model learning problem. Okay, just a small comment. Okay, let's go ahead. Group C, guys. Is Group C ready?
Hello, teacher.
Yes.
Yes. Can you hear me? Can you hear me?
Yes.
Yeah, and there's some problem in our group because like most of my group member need to make a PowerPoint thing that we have to do the presentation next week, so we don't have a PowerPoint yet. We don't have PowerPoint.
Just tell me. We can present this. Just tell me. So you guys finished it. You guys finish everything. Do you have a collab that you can show me maybe, so I can just see what you guys have been doing?
Collab. I can tell you what I've done and how to have it done, because my part is about the SPD part.
Project the collab. I can project, and you can keep talking about.
Or can you help me to show the collab, because I'm using phone now.
Of course.
So wait a moment. Well, as my part, I do the SPD part, and the SPD was for the low rank approximate expressed as R equal to U U sigma VT, something like that. And I choose the latent vector count of K equal to 50, meaning we implement as a truncated SPD because we want to make it high efficiency. So I only choose K equal to 50 to do the test. And we associate the SPD model's performance using 5-fold cross validation. I use the RMSE and MAE, and the result is 0.332 and show 0.6.
You're breaking up a little bit, I think. Yeah, let's up.
Okay, RMC is quite large, bigger than MAE. So maybe there are some outliers in our data sets. Okay, and however, when we use the PDA, I do a PCA in the following. Maybe in the collab you can see, but like, I don't know why there. I don't know why there's no picture, but however, I do the PCA, and the result shows that there's a dense region in the 2D space. No matter it was a user visualized result or item visualization results. And then using the K-mean clustering by the K equal to 5, and the output will see some feature on the here. So you can see some dense part on the space on the 2D charts. That is one part of SPD.
Yeah. So guys, the previous group, right? Okay. Let's see the PCA. Let's see the PCA, guys. Can somebody tell me about the PCA part?
Yeah, so I did the PCA part. I'm honestly not really sure with the results, but we can go to the code cell
Yeah.
11.
Yeah.
Yeah. So actually we did comparison between SVD and PCA, and what I found from this is that PCA actually doesn't do clustering that well compared to SVD, and you can see through the user latents, where basically in the PCA side it is the clustering is like all very close to zero, and you can't really tell that there's a very specific like group of people.
Yeah,
Like
that's what
group
we were saying before. Go ahead.
group of movies compared to like using SVD, where you can see that there are some clear trends, like the blue cluster, where it's like all of them are close, forming like a line similar to that. Yep. And even
But also
and
because, listen to me. So because you did the clustering over 2 dimension and over to higher dimension, because usually the good thing is to do the clustering for higher dimension, and then you represent the clusters in 2 dimension. If you cluster in 2 dimension, everything has been, beaten down, right? Everything has been reduced to such a slow dimension that it's hard to find clusters, right?
yeah, it should be multi-dimension, if I'm not wrong.
Good.
Yeah. Yeah. So the way that and then some of the results that we have below that is that SVD has a higher RMSE than PCA, but that doesn't mean that PCA is necessarily better than SVD. So some of the challenges I think is because it's just how PCA and SVD works. So PCA needs to center the matrix. So basically in this case, for user means like basically it is a very sparse data set, because it is unrealistic to expect all users to rate all movies, because the users will probably only rate the movies that they have watched. So what PCA does is that it sort of fills in with the average, or fills in with zeros, and what this does is that as a result, it makes the variance of like basically PCA is supposed to find like meaningful variances, and like this kind of destroys that, because like if you put everything with zeros or the average, it doesn't really that means any variances will be sort of like very dumbed down, and like it doesn't help with, like it doesn't basically does what PCA aims to do. Yeah, compared to SVD, where basically you're not filling in with like the means and averages, so it directly decomposes the matrices in this case. So the interaction patterns are much more well defined in SVD. Yep. So that is the results and analysis I got from PCA side.
Okay. NMF, you also did NMF, right? Any nice pictures? Yeah, let me see this. Oh, okay. Train and test NMF, as we were saying before, right? This idea that there is train and test is there. So what is latent 1, latent 2 embedding for k equal to 20? Sparsity distribution, active factor per user. I like that. I like that one there. Okay, go ahead, guys. Regularized NMF, it's gonna be nice. Okay. Poisson MF factorization still too. That's good. Train and that's good. It's good. Go ahead.
We haven't finished covering part 6 and 7.
Okay, very good. So I'll see you guys next week. And are you going to be able to submit the report in time, though, right? You can submit the report.
Yeah.
Okay, very good. Looking forward to next week. Okay. Group C will report next week. Okay. Let's see. Group D. I think they also have something to share. Group D, but not the full presentation. Group D. Because I think Group D we discussed a little bit. Yeah, just come say hi, Group D, basically. I just want to know if the leader is here today. If the people from Group D are here. Group D. Is anybody from Group D here? Group D is a little bit okay, go ahead.
So we are talking about the presentation here, right?
Yeah, just show me what you did so far, and then next week you'll be the I would say that you are the emerging leader, so you can lead the next week the presentation. Just show me what you did this time. It's okay, yeah. A leader has emerged.
So the progress isn't looking really good so far. So so far I've done importing the data and try to do the first part of like doing the PCA with SVD, but I have some little problem understanding what actually should be presented here.
In which sense?
Like I'm still fixing some of the part here, but I'm trying to do a PCA part here. But anyways, I'll try to do as much as I could here.
Mm-hmm.
Yeah, and that's pretty much what we have so far.
Okay, very good. But please try to be active, right? So I think, I think you can lead the effort this time, and try to, because I think you realize that people need to be active for the job to be done. So try to take that role and try to push everybody, and I'm sure that by next week you're gonna have a banging presentation. Okay, Group E guys.
Hello.
Hello.
There we are.
Here we are.
Let's start presenting. We did
Only
as well.
24 slides, guys. Only 24. I'm not sure.
We started as well the PDS challenge, and we finished it. I think. Wait, I will put it on big screen.
Very good.
Yes. This. Task 2. Wait 1 moment. Sorry for the SVD. Singular value decomposition. In task 2, we wrote a singular value decomposition baseline to predict movie ratings on places that are not yet filled in the dataset. You have like a matrix, and we filled the matrix on places which are not filled yet, like the non-filled places. First, we loaded the dataset. After this step, we filled all missing values with the total mean. This differs with PCA, which I will discuss later. After we have done this, we made a new matrix that compresses the matrix in a smaller matrix with K is 50. So it takes 50 most important futures. After this step, we rebuilt the full model with only these 50 futures. This new matrix contains the model's predictions. And finally, we calculated the root mean squared error, which came in at 0.67. 0.67. This means like on average our predictions are 0.67 of the real values.
Okay.
You can see in the graph over here, you see like the values on the x-axis, you see the original assessment, and on the y-axis you see the predicted assessments. You see our predicted assessments follow a positive curve, which is positive. So it predicts at least some of the values. Now we will move on to task 3, principal component analysis. For this, there's a big difference between SVD and PCA. PCA takes the global doesn't take the global efforts, but takes a local effort. So the efforts of each movie. So, and that fills in the non-filled in errors. So yes, the non-filled positions in a matrix are filled with the movie-specific efforts. Furthermore, the root mean squared error came in at 0.71, which is lower than the root mean squared error of SVD. So this means this analysis tool is better. And furthermore, we made a clustering. It's grouped in 5 clusters, as you can see. Purple, blue, and yellow are the main users, and the green and light blue are the outliers.
Again, so as I said the other, so here you did the clustering over 2 PCA dimension, right? What you can do is that you can choose K to be a much larger number, and you do clustering over this larger dimension, and then you project down the clusters on the on PCA2. This is much more informative than this, because if you do clustering over the data when it's so clustered, the clustering algorithm will just slice it equally. Yeah, we'll just slice it according to some geometric partition, basically. Yeah.
So bigger K gives more information, and then
basically, right? If you use just 2 PCA dimension, and everything gets punched down. So because ideally, right, these clusters, they live in high dimension. I mean, they live in some higher dimension, so they can be divided by hyperplanes. Okay.
Yes. Yeah, you can get more information on each cluster, right?
Correct. Yeah. If you scrunch down everything to 2D, then whatever the geometry in the higher dimensional is, just get flattened on the 2D plane. So you understand that simply geometrically, you don't have that many ways of separating the data, right? Sometimes you're lucky and the separation of the data is really effective, but of course,
yeah,
you know,
that's good to know. Furthermore, we interpret the cluster. The outliers that were, I think, if I say correctly, light blue and green, were obscure fans or art house fans. We did this with analysis. I didn't put this in the PowerPoint yet because I've just finished it an hour before class, this part, because I forget this part and I saw, maybe this is handy to do some analysis about it than just random things, to put just random things in. And furthermore,
I appreciate the honesty. Okay, I give you a job, but you forget about it. I appreciate it. Go ahead.
And furthermore, the mainstream, we took like the analysis not of the most liked films, but mainly of the most disliked films, because the most liked films were all over the place and I couldn't find any analysis about it. And they dislike the typical bad drama movies from the 90s. Now we move on to non-negative matrix factorization, which my teammate will do.
Okay, so in this section, we apply non-negative matrix factorization, in short NMF, to the MovieLens dataset. So unlike SVD and PCA, NMF constrains all components to be positive, giving us additive and interpretable latent features. For example, how much a user likes action or romance. So you can see that we apply NMF to 4 different K values, which is 5, 10, 15, and 20. So as you can see from the table on the left, as NMF increased from 5 to 20, the RMSE improves steadily, reaching its best RMSE of 0.6646 at K goes to 20. So you can see from the 2 data below for SVD and PCA, SVD achieves slightly better numerical RMSE, while PCA performed poorly due to its lack of non-negativity handling. So despite this, NMF offers better interpretability. We can actually read its factor as themes or genres. So you can see on the right, the table on the right, we have some examples of top movies in some of the latent factors. So for example, in latent factor 1, you can see the Terminator, the Crow, and the Santa Claus. So these movies are classified under theme of action or fantasy. So this gives us a better, clearer view of what each latent factor represents. So next. So okay, so now we will see on the left, we are visualizing the user embeddings for NMF where k equals to 20. So the x and y axis represents the first two latent features that were discovered by the NMF algorithm. So in the user embedding plot, you can see that most of the users are clustered near to the origin. This suggests that these users have fairly balanced preference across the various latent features, such as
let me stop you here a second. Just too many things in my brain. So here, what you did is just you represented the first two dimensions of the k equal to 20 representation, correct?
Yes, correct.
Very good.
Yeah, because for graphical representation in 2D, it's easier to show like 2 by 2
Well, I was wondering if you
multi-dimensional.
I was wondering if you redid the NMF decomposition of the k equal to 20, okay? And I was thinking this because I think group B, that's what they did, right? So it was confusing, and but I didn't want to anyway. Didn't want to comment too much on their presentation. But basically, they did NMF k equal to 20, and then they did PCA to represent the NMF components, which was a little bit of a jump in between low-dimensional representations. Just let me think a second, right? Because what they did was a little bit meaningful. Was meaningful in the sense that even if you have an NMF approximation, you could take the matrix approximated by NMF and see what are the two PCA dimensions that are dominant. Because here in this case, you just select the first two components, and we have no particular expectation over the clustering over the first two components. Are the yeah, that's it. Go ahead, please, go ahead.
Yeah, so
you understand my point, right? You understand my point?
Okay, so as what I explained previously, so you can see that most of the users clustered near the origin suggest that they are fairly balanced preferences across the two latent features. But however, there are some that users are positioned further away from the origin, indicating a stronger preference towards the specific latent features, which is a certain genre or certain theme. So these users are outstanding because their preference are more pronounced along certain axes, making the rating behavior more distinct and specialized. So basically, if they are more extreme towards latent feature 1, so when they view movies that are related to this latent feature, they will more likely to give a higher rating. Yep.
Very good.
Yeah. So haven't finished. Can go back. Yeah. So in the right, you can see the item embedding port, which is similar to user embedding, but this represents the different movie instead of different users. Yeah. So they represent equal things. Yeah. So in summary, the MMF model helps to uncover hidden additive patterns in user preference and item preference and allow us to clearly differentiate user and item based on their ratings behavior. This can particularly useful in a recommendation system where personalized suggestion can be made based on these latent preferences.
Very good.
So next we have regularized NMF, and regularized NMF is different from NMF because it introduces penalty terms to the loss function to impose additional structure, improve generalization, or encode prior knowledge. With this, we experimented with different lambda values from 0 to 1.0, so from dense to most sparse. And we can see as lambda increases, the root mean square error rises from 0.665 to 0.930 due to reduced flexibility, while the mean absolute error slightly falls from 0.263 to 0.223 from smoother predictions. So when lambda equals to 0.1, it offers the best trade-off, minor accuracy loss, but much higher interpretability, whereas lambda equals 0 is dense and lambda equals 1.0 is overly sparse and undefeated.
Wait a second. Let me pass a second. So you say that the RMSE increases, but the MAE decreases, right?
Yeah.
That's not obvious, right?
Mm.
Let me think. It's very hard to compare the two losses, right? Because one is in power 2, the other one is. So, but what does it mean? It means that proportion. Wow, just a second. So RMSE decreases. So means that the errors, they are closer to the in L2 distance. They are yeah. Yeah, it's counterintuitive, right? Of course, you can have the two losses. They behave differently. It's just I cannot wrap my head around this, because when lambda is equal to 1, and then of course you have forced so many of the coefficients to 0, that is strange that the MAE will be decreasing. Yeah. Okay, let me just observe the sparsity, right? What does it mean? Tell me this. What does it mean that the sparsity of omega is equal to 1 for lambda equal to 10, lambda equal to 1? Means that it's all,
Sorry again.
go ahead. The last row of the column. Can you explain the
Oh,
last row?
the matrix is entirely 0 and sparsity equals to 1.
But then what are you predicting then if it's entirely 0, right?
That means that the model has been over-regularized, right?
But why is the MAE so small then?
I'm not too sure about that.
I think there is something fishy. Try to check.
Okay,
Because
all right.
if it's all, so if omega is all 0, then you're just predicting the average movie, right? So what is left? Why would the MAE be small, right? Yeah,
Okay, yes. I'll check on that.
Okay, go ahead.
Yeah, so next we go to the latent factors. So we compare the dense and sparse model with lambda 0 and lambda 1.0. And we can see that the overall insight is that dense model fits data better but with mixed signals, but the sparse model uses clearer patterns but at accuracy cost. Next.
Just stay there. There's a lot of text. Let me parse it a second. So this is top movies, dominant theme, interpretability, strength, weakness, top movies. So these are the top movies for latent factor 4 versus latent factor 3. So you aligned the factors, right? Or do this 3 and 4 and 3 and 4, do they have movies in common? No, they are two different factors. Yeah?
Two different factors, yeah.
So one, okay. Family friend, brother, and strength, blah, 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 okay. Overlapping general mixed factor, brother, for answer, dense model. Okay, good. Go ahead.
Okay, so next we look at the different clusters. So to evaluate this, we use silhouette score inertia. So silhouette score measures how close each point is to the points in its own cluster compared to other clusters, and the higher is better. And for inertia, it's a sum of squared distance between points and their assigned cluster centers, and lower is better. So as we can see, regularized NMF when lambda equals to 0.1 achieves the highest silhouette and lowest inertia, indicating compact and well-separated user clusters. Or standard NMF lambda equals 0 shows moderate clustering, as dense factors cause user overlap, while SVD performs poorly with highly diffuse clusters. So a moderate level of regularization improves clustering quality, yielding clearer and more distinct preference groups without collapsing information.
Yeah, so here you did PCA over the NMF terms. Yeah, good. Yeah. Okay.
Okay, next is the Poisson matrix regression. So we try to run Poisson matrix regression across different case, and as you can see, that might be a very high RMSE value, which might be due to the scale mismatch issue, which Poisson regression assumes actually count data which has no upper limit. So this might be an issue which caused the data RMSE to skyrocket, and also inflates the NLL, which is the Poisson basically likelihood that Poisson regression is trying to minimize. So next. So for try to combat this, I tried to scale try different types of scaling to the original data, and through the different scalings, the best RMSE produced was the scale to 0.4, even though the RMSE is still relatively large. So I believe this is because PMF doesn't it optimizes Poisson likelihood instead of RMSE, so the different training objective differs.
You go to MAE, right? You should look at MAE instead of RMSE, right? Because as we saw for the last challenge, right?
Yeah. Thanks. So
okay.
for the PMF, looking at the clustering for the within cluster variance of the user embedding, there's a much higher. It's much higher as compared to SVD and NMF. This might be due to the training objective mismatch, which also mentioned. Also the data conversion difference, as PMF trained on only sees user item in pairs that exist. Okay, as for the item embedding, it has a much closer within cluster variance as compared to SVD and NMF, because I believe due to the regularization that PMF uses, it pulls factors towards 0, and so it causes the shrinkage to be larger, and so the clusters to be smaller accordingly.
Okay, so now we move on to the final stage, which is evaluating how well each method performs, both in prediction accuracy and in revealing meaningful patterns in user preferences. So among the models, standard NMF with rank 20 actually achieved the lowest RMSE of 0.6646. However, when we introduced L1 regularization with lambda value of 0.1, we found a slight drop in accuracy, but a major improvement in interpretability.
Of course, cool.
Yeah, so PMF can't be directly compared to RMSE by RMSE because it uses a Poisson likelihood instead of square error. Next slide. To assess structure, we clustered the user embeddings with k-means. So the regularized NMF model gave the highest silhouette score of 0.62 and lowest inertia, showing compact and well-separated clusters. Dense models like SVD had diffuse overlaps, while sparsity in NMF revealed clear genre-driven preference groups. Interestingly, PMF scored 0.57 on the silhouette metric, which is better than dense NMF, showing that Poisson-based models can still cluster users meaningfully, though not as cleanly as the regularized NMF. Next slide. So our takeaway is that focusing purely on RMSE isn't enough. According to the Goodhart's law, once a metric becomes the goal, it loses meaning. So the best model is one that predicts well and also explains why. So in our case, regularized NMF with lambda value of 0.1 achieved that balance with accurate predictions and clear interpretable user movie clusters. Yeah.
Very good. Yeah, so try to figure out that the Poisson factorization issue so that in the final presentation you can add those points in. And then I noticed a similarity in accent in this group, guys. Were you clustered by nationalities or school of provenance by any chance? Is there a bias there that I notice, guys?
Must have been by chance.
Lied to my face. Yeah. By chance, completely by chance. Yeah, of course. What are the odds? Yeah. Okay. Very good, guys. Yeah. No more comment from my side. Okay. Very good. I think that's very good job. I mean, good job. Team members have something in common. Okay, very good, guys. I think everybody did well. I'm sorry again for Group D that was without leader, and Group C that fell behind. I just remembered that I'll assign a new challenge on Friday. Okay, then Gaida will open the submission of the report on Friday. So try to submit in time. And yeah, so it's a little bit unfortunate that we'll have 2 sessions in which you'll have to present your like you had only 1 week this time to prepare the challenge, and then we're back to back another challenge this week. Of course, again, it's my fault that I forgot to post, but you guys got to rest for 2 weeks, so maybe there is a balance there. And otherwise, yeah, good job to everybody. Sorry that some people run into the complication. Now we will give you only the intra-team evaluation because the inter-team evaluation is no longer there. The way you share the grade is uniform across the team members. And as usual, I'm going to be here for 10 minutes if you have any questions. Otherwise, we stop the recording now. We say hi to the people on YouTube, and we update next week. Okay?